What's up, guys? You may remember back in your grade school or preschool or maybe even junior high school days studying something related to the sun and the stuff around it. There's even nursery rhymes for it. It's like, have you ever seen a family, the sun and its planets? And that's exactly what we're going to talk about in this video. Welcome, Science Fam. My name is Sir Ramon and this is Science with Sir Ramon. Let's get right into it. So this is a picture of the solar system. And the solar system is basically just the sun and everything that revolves around the sun. Now, why is it an important thing to talk about the solar system? Again, in philosophy, supposedly people were wondering what's the center of this universe. People used to think, oh, maybe it's the Earth, a geocentric view. But then people eventually said, oh no, it's the sun that's the center of the universe. It's heliocentric. But now we realize that the sun is just a small part in a big, big game. Okay? But it's the center of our little solar system. It's us that revolves around the sun. Okay? So our solar system itself is a very small thing. It's very small. It's just a very tiny speck in the Milky Way. This is an artist's rendition of the Milky Way galaxy. Take note that any picture of the Milky Way galaxy is probably not the actual Milky Way galaxy itself. Okay? It's probably just the plane of the Milky Way galaxy. This is just an artist's rendition, but in this artist's rendition, there is, the sun and the solar system is probably just that tiny speck at the end of that arrow over there. Okay? Even if we zoom in into the pixels of this image, it's probably not even high enough resolution to justify that one pixel is the solar system. That's how tiny the solar system is. But condensed within our solar system revolves around the sun, or Sol, and it contains most of the mass and energy in our solar system. It also serves as the anchor that keeps us revolving around it. It's the anchor, the gravity of the sun anchors us in our orbit, Earth's orbit specifically. So again, since it contains most of the mass and energy of the solar system, all the energy on Earth technically comes from the sun. Okay? Most of it, at least. Some could come from asteroids hitting the Earth, but that's like negligible. So what are the things that orbit around the sun? There's lots of things that go around the sun, lots of things that are part of the solar system, but let's start with the OG, the subject of them nursery rhymes, the planets. Okay? The planets are basically large celestial spheres that aren't massive enough to become stars. Again, they don't have enough mass to start nuclear fusion. Again, stars are things that have nuclear fusion occurring in their core, meaning nuclei of atoms are mashed together, become heavier elements. So for your planets, we have the inner planets called the terrestrial planets. We're starting near the sun and we're gonna head outward. So let's get rid of my face. Okay. So first we have Mercury. It's the smallest planet. It's very, very near the sun, and it is blindingly fast in its orbit. 1 year on Mercury is just 88 Earth days. So it's super fast. Next we have Venus. Not be confused with the teacher. Venus spins slowly in the opposite direction. So if Earth is spinning in the way that the sun rises in the east, Venus, being hipster, spins slowly in the other way. And so it also has a thick atmosphere, making it very, very hot. Okay? The greenhouse effect makes it very hot, hot, hot. It's the hottest planet in our solar system. The combination between it being near the sun and having greenhouse gases makes it very hot. Next, we have Earth, our home planet. It's the only place we know of that contains life. And it's the only place we know of that... wait, no, it's not the only place. It's the only place in our solar system that has liquid water on the surface. Okay? So again, we're not sure if there's life on other planets so far. We've found water in other planets in different systems, very, very far from our own, so who knows, right? Next, we have Mars, or Mars in that one movie. Anyway, so Mars is a desert planet. It has a very thin atmosphere, and there's some evidence in the form of valleys and what looks like river basin systems and ocean basin systems that Mars was probably wetter and warmer and had a thicker atmosphere. Okay? Again, Mars was probably very different in the early stages of the solar system, but now it's just dust, and it's red because of the rust that's in the dust. Next, we've transitioned to the Jovian planets again, farther from the sun. These are very, very big. So Jupiter is the biggest one, and it is more than twice the mass of all the other planets combined, and it has a big red spot here. It's a permanent storm on the planet's surface. It's the biggest storm in the solar system. So big giant red spot. Here. Now we have Saturn. We put a ring on it because we like it. It has the most complex ring system among the planets, so it has a lot of ice in that ring system. So the other giant planets have rings, but they're not as visible as Saturn's very nice ring. Okay. Uranus, I'm not going to pronounce it the other way. Uranus rotates in a weird angle. It's a 90-degree angle. So if Earth spins like this, let's make it full. Okay, if Earth spins like this, tilted 90 degrees, that's how Uranus spins. Okay, it's about 90-degree angle. So it looks like it's just waltzing around like weird spinny way. So that's Uranus. Again, it also has its own rings, but they're not as distinct. We have Neptune, the 8th and most distant planet. It's very dark, it's cold, it has supersonic winds, and it was discovered using math. So don't discount math, guys. Math is important for discovering stuff. But wait! What happened to Pluto? What did they do to my boy? How come it's not a planet anymore? Pluto used to be my favorite planet. So Pluto is not a planet anymore, not just because it's small, but because of the formal definition of a planet. So after discovering several things, so after we designated, okay, there's 9 planets, and then eventually astronomers discovered other things in the asteroid belt near the orbit of Pluto that are around the size of Pluto but aren't considered planets. They realized, if there's lots of these things, it's either all of them are planets or Pluto isn't one. So everybody got into a debate like what even is a planet, and then eventually the International Astronomical Union settled on this definition. 1, it has to orbit around a star. Okay, so Pluto does orbit around the sun. It must be massive enough to be round because of its own gravity. So Pluto, yes, is a sphere because it has enough gravity to become a sphere. And number 3, it must have cleared the neighborhood around its orbit. What does that mean? It means it has to be the dominant thing in its orbit. There shouldn't be anything around the same mass or even around 50% of its mass in its orbit. It should be absorbed into that thing for it to be considered a planet. Now this is where Pluto fails. Okay? Pluto is a dwarf planet because it isn't the dominant thing in its orbit. It did not clear its neighborhood. It's within what is actually an asteroid belt, and it's actually sort of a binary system with its what used to be called its moon, but is actually now considered around the same size as it, so it kind of just flips around on itself. So it's Pluto and its moon, okay, all together. So again, it's a dwarf planet, and it's not a moon because it satisfies definition 1 and 2. Okay. So what about the fuzzy bits in the solar system diagrams? We have these things, these fuzzy wuzzies. Okay, these are basically disks and clouds. They are large areas of celestial debris, not just dust. There's also asteroids, and they are trapped by the sun's gravity. So they're still part of the solar system. So we have the main asteroid belt. It's found between the terrestrial and Jovian planets. And it has lots of asteroids, but even more space. So it's not an asteroid field that you know, if you were piloting a spaceship, you have to dodge and weave between asteroids. You actually have to aim in order to somehow land on an asteroid or hit an asteroid. So our probes, our space probes that cross the asteroid belt, they don't even have to dodge much because the asteroids actually are spread out amongst a very, very large space. Okay. Now, this asteroid belt exists because it's the leftovers of how the solar system formed. And we'll more on that later. Next, we have the Kuiper Belt. The Kuiper Belt is found at the orbit of Neptune and beyond that to up to 50 astronomical units from the sun. An astronomical unit is basically the distance between the sun and the Earth. If we take that distance, that's 1 AU. So, you know, we tend to use AU for distance, because it's the most familiar thing we have in the astronomical scale. Anyway, the Kuiper Belt is made up mostly of frozen methane, ammonia, and water, similar to what the Jovian planets are made of. Okay, because there's enough, it's cold enough, there's there's not enough heat for it to melt, so it can be frozen volatiles. Okay, and the Kuiper Belt is used to be considered the boundary of the solar system, but now it's not. We have the Oort cloud. It's a theoretical boundary of the solar system, and it's theoretical because we haven't actually observed it yet. We can't use telescopes to observe it because it would be too diffuse to be able to observe it using just a telescope. We need to get something there to see it, but unfortunately, we can't. Okay? It's theoretical. It was predicted using mathematical equations, and supposedly that tiny bit in the center with this orbit as well, that's the solar system. The Kuiper Belt is this thing, this diffuse thing, and the Oort cloud is this giant sphere. Okay? Now, Voyager 1, one of our space probes, is actually on its way to that area, to where the Oort cloud should be. It'll reach there in 300 years, but unfortunately, the generators that power it will die in around 2025 because there's no sources of energy near it for it to make more energy. So we won't even be able to get data from Voyager 1, but you know, Voyager 1 gets to experience the Oort cloud. Have fun, Voyager 1. Who knows if we'll even last 300 years as a species, right? So how did this solar system form? So it's our little corner of the galaxy, but then, you know, it's so arranged in a nice way. Did it start out in a special way? So, the main theory for that is the Nebular Theory. So it's the formation of a solar system. Take note that solar system can also refer to any system that has a star and the planets that orbit around it. Okay, so again, if it's not capital, it's a general system around a star. So a solar system can form from a nebula, and it assumes that the planets always form together with their star. So here are the steps for how to make a solar system. Okay, it's probably better than that how to make rice video. So step 1, we start with a nebula. So we have a cloud of dust and gases. Okay, so it's too diffuse for anything to happen with it on its own. So in order to make something with this nebula, we need step 2. We need to stir the nebula with what we call a gravitational collapse. It's a collapse because instead of being spread out and diffuse, it collapses in on itself. It turns into something that is more dense. So in order to do that, in order to stir it, we just add gravity through a passing star or a passing black hole. Oh yeah, sorry. Guys, black holes move. If you think they're just there, like holes, no, they actually move in space. Huh. So if it passes by, or if a supernova has the shock waves, move the particles in such a way that they clump up together, then it can trigger a gravitational collapse. So once you have that, you need to allow that matter to settle into a rotating protoplanetary disk. That's just a complicated way of saying that it swirls. So after it starts collapsing, it swirls around on a center. And as it swirls, that center begins to bulge. That bulging center, that big central ball, will eventually form into the star. While the disk of debris, again, there's usually a disk, you can see in the background is a big wide disk. That disk will help form the planets around the solar system. Step 4. You have to mix. Allow the protoplanetary disk to mix until clumps form due to what we call accretion. Accretion is a complicated term for clumping together. So the dust particles clump together. And as we all know, the more matter there is, the more mass there is, the more gravity there is. So anything smaller than that clump gets attracted by the gravity of that clump until it gets bigger and bigger. Okay? Again, it's a dust eat dust world out there. So accretion, big dust eat small dust, become bigger dust. Okay? It's just like that IO game, I forget. So the inner planets close to the sun could only form from the solids that are that have high melting points, like your silicates, rocky things. Okay? That's why the inner planets, the ones close to the sun, are terrestrial planets, because we need things that don't melt when they're this close to the sun. The outer planets are beyond what we call the frost line. So beyond that certain point, beyond that distance from the sun, volatiles can actually exist as solids. So your water, your methane, your ammonia can actually freeze into actual solids and become our Jovian planets. Okay? And Earth just so happens to sit in the nice green zone where we form from silicates, but there's enough distance to let water be liquid. not gas, not solid, but liquid. There's a very thin band where it can be liquid water. Alright, so step 5, once you have these accretion things, let those clumps bump into each other and grow into planets and moons. So as they bump into each other, the explosion of energy and debris can cause some smaller clumps to form into moons or satellites that orbit around the bigger clumps. Okay, that's why we have moons and satellites around our planets. And the leftover material after the planets and moons form will get sucked into certain places. The gravity of different planets will push the leftover material into the asteroid belts. That's why we have the main asteroid belt between the giant Jovian planets and the terrestrial planets. That's where the leftover material is, aside from the Kuiper Belt. Okay? And so basically, the greatest things can come from the humblest beginnings, whether it be the initial singularity of the universe or the nebula, the diffuse stardust. That is the nebula from which our solar system sprang from. Okay? The biggest things can come from the smallest things. From dust and gas, we get planets, galaxies, and stars. And so the question left is, how will you expand your known universe? What greatness can you achieve before you eventually become space dust again? Okay? We'll find out perhaps in the next lessons. So this is the end of this set of lecture videos. I'll see you guys next time.